Hello, and welcome to Whispers of Earth, a quiet place where curiosity slows down and the vast, ancient planet beneath our feet becomes the perfect story for drifting minds. Tonight, we'll journey so far into the past that even the oldest stones struggle to recall it. We're traveling to an age before forests, before seas as we know them, before the moon shone with its familiar face. A time so foreign it feels less like Earth and more like another world entirely. This is the Hadean Eon, named after Hades, the underworld of Greek myth. Not because it was sinister, but because Earth in its infancy was a restless, fiery child throwing tantrums in magma. But what would it really have felt like to stand, or more accurately float, in such a place? Solid ground was nearly non-existent on this half-formed sphere. Did water exist? Was there even an atmosphere, or anything resembling a sky? And while we imagine all this, I wonder where you are this evening, what time it is in your part of the world. Fitting, isn't it, that we're talking about a period before clocks, before continents, before breath itself. And here you are, in the distant future of that very Earth, listening quietly. If you find this wander into deep time calming or thought-provoking, it would mean so much if you left a like or subscribed. That way, others in search of a gentle pause might find this space, too. So, take a deep breath, let your thoughts loosen, and let us begin. Because before any story of life could be told, before trilobites, dinosaurs, or even the first fragile microbes, there was only heat, stone, and silence. About 4.5 billion years ago, Earth was born not with serenity but with upheaval. It emerged in violence, shaped by collisions and chaos. This was not the tranquil blue planet we know, but a blazing sphere of molten rock and metal. Yet within that storm of fire, the first hints of oceans, continents, and eventually life itself were beginning to take root. How did something so severe become the only world we know that nurtures life? That's the mystery before us. Sometimes, answers begin not with fireworks or fossils but with something subtle, a flicker in a compass needle. Among the ancient rocks of the Canadian Shield, geologists once noticed something peculiar. They were studying tiny zircon crystals, grains so small they could rest unnoticed in an eyelash, when their instruments hinted at something unusual. What they found would challenge everything we thought we knew about Earth's earliest chapter. For generations, the Hadean was imagined as a geological blank spot, a void. A time when Earth melted and remelted itself so often that no solid record could survive. A chapter seemingly erased from the planet's memory. But then came the Zircons. These crystals, nature's toughest little timekeepers, were discovered in rugged places like the Jack Hills of Western Australia. Against all expectation, they turned out to be not just old, but unthinkably old, over 4.3 billion years in age. Inside these grains were secrets. Zircons form in the presence of granite and water, not the raw lava of volcanoes, but the slow, patient cooling of continental crust. To find them at such an early date was like stumbling on a glass of iced tea inside an inferno. Impossible. And yet, here they were. Their isotopes whispered of liquid water, oceans, perhaps, existing at a time we once thought Earth was nothing but flame. Scientists like William Peck and Simon Wilde studied these crystals with lasers and spectrometers, atom by atom. Slowly, the picture of the Hadean shifted. It wasn't only fire and destruction. For brief moments, Earth may have been calmer, more Earth-like than we imagined. Somewhere in that half-billion years between Earth's fiery birth and the rise of stable crust, rain may have fallen. Rivers may have flowed beneath a fragile sky. It's strange, isn't it? The key to understanding Earth's first steps lies not in vast landscapes or deep trenches, but in grains of crystal smaller than sand. These tiny relics became our most trustworthy witnesses. Patiently, they survived while continents rose and sank, while oceans evaporated and reformed. They endured, and in them the memory of a young Earth persisted. To imagine the Hadean is to set aside everything we know about Earth today. Picture a sky not blue, but thick and poisonous, filled with carbon dioxide, methane, and sulfur gases. Sunlight struggled to pierce that haze, filtering down like amber syrup. The ground glowed with molten rivers of rock that cracked and reformed as though the entire surface were a boiling soup just starting to cool. For ages, the sky itself may have shone faintly with the light of constant fire. After its formation, Earth endured a gauntlet of impacts from comets and asteroids, a period called the Late Heavy Bombardment. For hundreds of millions of years, collisions scarred the surface, sometimes vaporizing whole oceans or blasting away chunks of atmosphere. Yet somehow, through this endless barrage, something endured. One hauntingly beautiful idea is that one colossal impact created our moon. According to the giant impact hypothesis, a Mars-sized body, called Theia, smashed into young Earth with such force that both worlds partially melted. Debris was cast into orbit, where it slowly gathered into a glowing disk that eventually coalesced into the moon. If true, every moonrise is a memory of Earth's most violent day. That event did more than craft a companion in the sky. It may have tilted Earth's axis, giving us seasons. It may have stirred the molten core, sparking the magnetic field that now shields us from solar radiation. And after this chaos, Earth began to settle. Steam condensed into torrential rains. Oceans pooled in basins. The rock cooled enough to remember. In these calmer corners, zircons formed, tiny sparks of clarity amidst a world still thrashing through its infancy. The Hadean wasn't purely hellish. It was a paradox, a balance of cataclysm and creation. Even as molten rock flowed and impacts raged, Earth was beginning to sort itself. Heavy metals like iron and nickel sank inward, forming a core. Lighter elements floated upward to create the mantle and crust. With this differentiation, Earth was no longer just a random mass of rock, but a layered system with structure, and a future. From this came a magnetic field, faint at first, but growing stronger, a shield against the solar wind that would otherwise strip the atmosphere away. The atmosphere that clung to the planet was nothing we could breathe. It was thick, toxic, heavy with greenhouse gases. Temperatures on the surface soared to hundreds, even thousands of degrees. Lava plains stretched for miles, interrupted only by impacts that melted the crust anew. Yet over time, steam condensed, clouds formed, and rain began to fall. Not a gentle drizzle, but ceaseless torrents lasting centuries, maybe millennia. Rain hissed on hot stone, boiled on contact, but never gave up. Pools formed, then lakes, then oceans that slowly spread across much of the surface. And with water came possibility. These early oceans were acidic, filled with iron, sulfur, and chemicals leached from crust. No coral reefs, no plankton, just a simmering broth of raw chemistry. Yet in this restless mixture, something remarkable began, the ingredients of life. Along hydrothermal vents, where volcanic heat met seawater, molecules assembled, chains of carbon, primitive amino acids, lipids. They were not alive, not yet. But they were the alphabet. Life would be the sentence. All the while, Earth was still under bombardment. Some impacts wiped out oceans in an instant. Yet they may also have delivered gifts, organic molecules carried by meteorites, precursors to RNA, even water-bound in comets. In this way, Earth's earliest age was both a battlefield and a laboratory. Destruction and creation worked hand in hand, each cycle pushing the planet closer to balance. By around 4 billion years ago, patches of stable crust may have emerged. Not continents as we know them, but small granite plateaus that resisted erosion. Above them, skies began to clear. Oceans deepened. Chemistry grew more complex. And perhaps, in those quiet corners, life itself stirred. We cannot know for certain. The fossil record of this time is nearly erased. Rocks were melted, crushed, recycled. But subtle signatures remain, carbon isotopes that hint at biological processes as early as 3.8 billion years ago. If true, then life arose not after chaos, but within it. Fragile cells may have clung to hydrothermal vents while fire still rained from the sky. The Hadean, once thought to be a wasteland, was not barren but dynamic. It was a crucible of fire, water, and stone, constantly testing, constantly reshaping. Out of that turmoil emerged a planet that would one day support forests, oceans, and breath. To picture Earth during the Hadean is like trying to recall a dream you never had. There were no forests to sway in the wind, and perhaps no wind at all. No continents stretched across the globe, no gentle beaches marked the edge of seas. Instead, the world was a restless stage, caught between solid and molten, between forming and collapsing. The surface was a patchwork of magma plains, volcanoes, and half-cooled crust drifting like rafts across a fiery ocean. The young Earth had only just finished its assembly, sweeping up cosmic leftovers from the birth of the solar system. It was still unsteady, still learning how to hold itself together. Imagine a sky the color of rust, dense with carbon dioxide, methane, and hydrogen sulfide. The air was heavy, oppressive, and yet it was the beginning of something essential, the first atmosphere. Toxic though it may have been, it was a start. Temperatures were blistering. Lava bubbled across the surface, only to be shattered by another impact from the sky. Rock melted, cooled, and melted again. The planet seemed to breathe in fire. And yet, within this storm, change was underway. Earth began to organize itself. Deep inside, metals separated, iron and nickel sank to the core, while lighter minerals floated upward to form mantle and crust. This differentiation gave the planet an identity. For the first time, Earth was not simply a molten ball, but a layered system. With a metallic core came a magnetic field, weak at first, but gradually strengthening. That invisible shield allowed an atmosphere to cling to the planet rather than be stripped away by solar wind. The skies, meanwhile, were beginning to fill with steam from volcanic eruptions. As the surface cooled, condensation began. And then, at last, it rained. Try to imagine it, the very first rainfall on Earth. Not a gentle spring shower, but sheets of water pouring down for centuries. The ground hissed and smoked, trying to resist, but the water persisted. Slowly, pools collected, lakes formed, and eventually vast oceans spread across the world. Dark, hot, and acidic, these seas would have looked nothing like the blue waters we know. But they were the stage upon which life's story would one day begin. Beneath those early oceans, volcanoes still erupted, releasing gases and minerals. Hydrothermal vents spewed hot fluids rich with sulfur, iron, and other elements into the sea. These places became crucibles of chemistry, where simple molecules assembled into more complex ones, amino acids, primitive lipids, and carbon chains. They were not alive, but they were becoming the raw vocabulary of life. Meanwhile, Earth endured the relentless storm of the Late Heavy Bombardment. For hundreds of millions of years, space hurled debris at the planet. Some collisions boiled oceans away, some stripped away air, but others brought precious cargo, organic molecules, icy water, and carbon compounds. It was destruction, yes, but it was also delivery. Catastrophe seeded creation. The Hadean was not a quiet age, but it was a productive one. Each cycle of violence pushed Earth closer toward balance. Rock hardened into the first durable crust. Oceans deepened and stabilized. The atmosphere, though still hostile, began to shift. And in that changing world, chemistry turned toward complexity. It's easy to imagine the Hadean as a wasteland, but that sells it short. There was energy everywhere, heat, pressure, gradients of chemistry. There was motion, continents hinting at their first forms, volcanoes building islands only to tear them down again. There was resilience, the stubborn persistence of oceans reforming after every catastrophe. By around 4 billion years ago, Earth's surface may have hosted small, stable patches of granite crust. These were not yet continents, but they were the bones of what would one day become land. Above them, the atmosphere thickened. Below, the oceans churned with minerals. Somewhere in this restless mixture, the possibility of life was growing. The truth is, we don't know exactly when life began. The record is scarce, buried beneath eons of destruction. Yet whispers remain. Certain isotopes in ancient rocks suggest biological activity as early as 3.8 billion years ago. If that's true, then life didn't wait for Earth to be calm. It emerged in the chaos, clinging to vents and chemical gradients while the surface above was still being bombarded from space. And even if life had not yet taken hold, the conditions were ready. Meteorites carried the seeds of organic chemistry. Hydrothermal vents created pockets of energy and minerals. Oceans dissolved elements into chemical soups. Rainfall weathered rock into ions that flowed back into the sea, changing the very chemistry of the water. Slowly, patiently, Earth was writing the recipe for life. It's humbling to think of. This planet, once a blazing sphere of molten rock, now had oceans, an atmosphere, and even the beginnings of land. Its core pulsed with energy, its crust shifted with tectonic stirrings, and above it all, storms raged across skies tinted red by methane. It was harsh, yes. But it was also hopeful. The Hadean wasn't simply a story of fire. It was a story of transformation. Catastrophe followed by renewal. Impact followed by rain. Collapse followed by rebuilding. A rhythm that would repeat across the ages, shaping the planet again and again. And as the Hadean gave way to what would follow, Earth carried forward not just scars but lessons. It had learned persistence. It had learned balance. And in that persistence lay the possibility of something entirely new, life. The story of early Earth often feels like watching an artist at work, furious strokes of color across a canvas, only to scrape it clean and begin again. After the Hadean's fiery infancy, another chapter of violence arrived, the Late Heavy Bombardment. The name itself sounds like an artillery campaign, and in many ways, that's exactly what it was, except the battlefield stretched across the entire solar system. Hundreds of millions of years after the planets first formed, our cosmic neighborhood was still cluttered. Leftover fragments of rock, ice, and dust wandered in chaotic orbits. Gravitational tugs from the giant planets stirred them constantly. The result? A cascade of impacts that rained down upon Earth, Venus, Mars, and Mercury. Some of these intruders were small, boulders no bigger than a house. Others were monstrous, the size of mountains or even small continents. Each time one struck Earth, the results were devastating. Oceans boiled in an instant. Atmosphere ripped away into space. Crust shattered and melted. Shockwaves raced across the globe. It wasn't one event but a relentless storm, stretching on for eons. And yet, as paradoxical as it sounds, this bombardment may have been constructive as well as destructive. Each impact didn't just erase, it created. Craters cracked the crust, opening pathways for magma to rise, for gases to escape, for water to seep into rock and cycle back out. These processes may have helped establish plate tectonics, the great shuffling of Earth's crustal plates that drives mountains, volcanoes, and continents. Without tectonics, Earth might have become stagnant like Venus, smothered beneath a suffocating shell of rock. With tectonics, however, Earth became alive, restless, shifting, and ever-changing. Impacts also stirred the oceans. Every strike vaporized rock and seawater, triggering chemical reactions that released minerals and reshaped the chemistry of the seas. Hydrothermal systems flourished, filled with gradients of temperature and chemistry, perfect laboratories for complex molecules to form. Some scientists believe the very ingredients of life may have been delivered by these space rocks themselves, amino acids, carbon compounds, even precursors of RNA. In this way, destruction and creation danced together. Earth was being pummeled from above, but prepared from below. Each catastrophe enriched the recipe for what was to come. And amidst this chaos, hints of something extraordinary may have begun. Carbon isotopes in ancient rocks suggest that as early as 3.6 billion years ago, life might already have been flickering. Not proof, but whispers, a skew in carbon ratios here, a layered structure there, traces that look suspiciously like microbial mats fossilized into stone. If true, then life was already underway while the sky was still falling. It's a striking thought, that the earliest cells did not wait for calm seas or gentle skies. They emerged in the thick of catastrophe, opportunistic, resilient, finding niches where energy and chemistry aligned. Some may have clung to hydrothermal vents, protected from impacts above. Others may have survived in cracks and pores deep within the crust. This resilience wasn't just luck, it was the beginning of a pattern. Earth would endure mass extinctions, ice ages, and catastrophic volcanism in ages to come. Each time, life would adapt, survive, and reshape the planet again. That rhythm began here, in the chaos of the Hadean and the storm that followed. But even as we look for life's first flickers, we must remember, oxygen was not yet part of the picture. The atmosphere was still a greenhouse haze of carbon dioxide and methane. The seas were acidic, greenish or rust-colored with dissolved iron. But tiny changes were underway. Some zircons suggest that trace amounts of oxygen existed locally, perhaps from sunlight splitting water molecules high in the sky. Later, perhaps much later, microbes would harness sunlight directly, exhaling oxygen into the oceans. But even in the Hadean, oxygen whispered faintly of things to come. Meanwhile, deep inside the Earth, currents of heat churned the mantle. These convection cells dragged thin slabs of crust above, moving them slowly across the surface. Here, we see the birth of plate tectonics, not yet the grand collisions that would one day raise Himalayas, but subtle shifts and subductions. This recycling system gave Earth something no other planet seems to have, a planetary thermostat. Carbon dioxide was drawn into oceans, weathered into rocks, then recycled into the mantle. Without this balance, Earth could have frozen solid or overheated into a Venus-like nightmare. Instead, the planet adapted, slowly but relentlessly. And as tectonics deepened, something new emerged: land. Not continents as we know them, but small proto-continents, patches of silica-rich granite that resisted erosion. These cratons, some of which still exist today as the cores of continents, were the first land masses to rise above the waves. Though small, they mattered enormously. Land changed everything. Rain could strike rock, breaking it down grain by grain, sending minerals back to the sea. Shallow coastal zones formed, rich in nutrients and chemical gradients, perfect laboratories for future life. Even the act of erosion was transformative. Rain carried calcium, potassium, and magnesium into the oceans, altering their chemistry, providing the very elements that cells would later need. Earth was, without knowing, writing the recipe for life one mineral at a time. And somewhere in those restless seas, chemistry turned toward biology. Imagine a simple bubble of lipids forming, enclosing a droplet of water. Inside, a few organic molecules swirled, amino acids, perhaps, or a strand of RNA. The bubble grew, divided, copied itself imperfectly, and in doing so stumbled into something remarkable: survival. It wasn't yet life, not fully, but it was close. Evolution had begun its long story. This transition was not sudden. It wasn't a single spark, but a cascade of small steps. Chemistry became complexity. Complexity became replication. Replication became evolution. And from there, the story would never turn back. Even as chemistry edged closer to biology, Earth remained a restless stage. The crust thickened here, cracked there, tugged by the slow ballet of tectonics. Volcanoes erupted both on land and beneath the seas, sending out pulses of basalt that spread across the surface like fresh scars. Oceans deepened, filled with minerals leached from rock, and over them a heavy sky of carbon dioxide and methane held in the warmth. Yet within this apparent chaos, cycles were beginning to emerge. Rain weathered rock, carrying dissolved minerals into rivers and back into the seas. Carbon dioxide from the air mixed with water, forming carbonic acid that etched stone, pulling more carbon out of the sky. The hotter the planet grew, the faster weathering drew carbon down. The cooler it became, the slower the process. Without life's hand, Earth had invented a feedback system, a planetary thermostat, the carbonate-silicate cycle, that would keep the world within habitable bounds for billions of years to come. This was stability born not from peace but from tension, a balance between fire within and water above. And it created the backdrop against which life could attempt its first experiments. Imagine those early seas, dark, acidic, loaded with dissolved iron, bubbling with volcanic gases. Not friendly by our standards, but rich in opportunity. Along hydrothermal vents, minerals precipitated from hot fluids, forming chimneys that spewed water superheated and enriched with sulfur and metals. In these strange environments, gradients of heat, acidity, and chemistry provided energy for molecules to self-organize. Lipids formed bubbles. Carbon chains lengthened. Nucleotides began to assemble. At some point, perhaps in a quiet tide pool or in the depths of a vent, replication began. A strand of RNA, fragile but functional, made a copy of itself. The copy contained mistakes. Some were useless, others destructive, but occasionally one made survival just a little easier. That was enough. In the endless trial and error of chemistry, evolution had entered the stage. The earliest forms of life, if we can call them that, needed little of what we take for granted. They required no oxygen, no sunlight. They thrived on gradients, of temperature, of acidity, of chemistry. Some may have consumed hydrogen or sulfur, exhaling methane or other gases into the sea. In doing so, they began to alter their environment, not with intention, but as a side effect of metabolism. New niches appeared, new gradients formed, and slowly a web of interactions emerged. Ecology before ecology had a name. And then, perhaps in a shallow sunlit bay, something extraordinary happened. A microbe stumbled upon a way to capture sunlight. Not yet the oxygen-producing photosynthesis we know today, but a simpler process, using light to drive chemical reactions. Eventually, this too evolved into a more powerful form, oxygenic photosynthesis. These tiny pioneers, ancestors of today's cyanobacteria, released oxygen as a waste product. At first, the ocean soaked it up like a sponge. Iron dissolved in seawater rusted, forming the striking banded iron formation still found in ancient rock, layers of red and black stone, the fingerprints of the planet's first breath of oxygen. But the ocean could only absorb so much. Once saturated, oxygen began to seep into the air. At first, it was only a trace, too little to breathe, but enough to change the rules. Oxygen oxidized rocks, stripped methane from the sky, cooled the climate, and began building ozone high above, a shield against ultraviolet radiation. This trickle of oxygen carried with it both promise and peril. For future life, it would be liberation, a fuel source more powerful than any before it, allowing cells to generate far more energy. But for the organisms of that early world, oxygen was poison. It corroded proteins, interfered with metabolism, and threatened survival. The planet was entering the long lead-up to the Great Oxidation Event, one of the most consequential shifts in Earth's history. And yet, even as life experimented with light and oxygen, Earth itself was far from stable. The planet still shifted restlessly. Continents collided and tore apart. Volcanoes erupted in cataclysmic floods, pouring out vast provinces of basalt that could reshape climate for millennia. Some eruptions released carbon dioxide, driving the world into hothouse warmth. Others filled the skies with sulfur aerosols, dimming the sun and plunging the planet into cold. At times, the cooling may have gone so far that ice reached the equator. Imagine Earth as a snowball world, oceans sealed under frozen shells, continents blanketed in white. If life existed then, and evidence suggests it did, it would have clung to hydrothermal vents, to subglacial refuges, to tiny oases of liquid water. Survival meant adaptation, again and again. But the planet never remained frozen forever. Volcanoes continued to belch greenhouse gases into the air. Slowly, carbon dioxide built up, the ice melted, and oceans opened once more. Cycles of freeze and thaw, collapse and renewal, became woven into Earth's fabric. Each cycle transformed the environment and forced life to respond. Some microbes perished. Others found ways to endure. A few even thrived, discovering new metabolisms and pathways. Out of hardship came innovation. This rhythm, expansion, collapse, adaptation, would repeat across Earth's entire history, from the tiniest microbes to the mightiest animals. And through it all, the moon still circled overhead, closer then than it is today. Its pull stirred the seas, driving powerful tides. These wet-dry cycles along coasts and tidal pools may have been critical for life's chemistry, concentrating molecules, drying and rehydrating them until complexity took root. Even now, the moon drifts a little farther away each year, but its influence on tides remains, a constant reminder of the intimate role it played in Earth's beginnings. By this time, the Earth was no longer just a world of geology. It had become a biosphere, a place where rock, water, air, and life interacted, inseparable from one another. Microbes altered the chemistry of oceans and skies. The land shaped the evolution of life, and life in turn shaped the land. The seas, once green or red with dissolved iron, began to clear. With oxygen rising and iron settling out, the waters may have turned the blue we now know. The sky too shifted, from a hazy orange to a pale blue dome, tinted by ozone. The planet was not yet the one we recognize, but its outlines were emerging. Still, life remained microscopic. Cyanobacteria formed layered colonies called stromatolites, dome-like structures of mucus, minerals, and microbes. Slowly, layer upon layer, they recorded their existence. We were here. We made oxygen. We endured. Some of these structures still exist today, ancient echoes of the first great ecosystems. Meanwhile, Earth's crust continued to grind and rearrange. Subduction zones dragged slabs of crust into the mantle, recycling rock and gases. New ocean ridges produced fresh seafloor. These processes tied together the biosphere and the geosphere, linking life and land in cycles that continue today. The Earth was no longer just a restless rock orbiting the sun. It was a system. It was alive with interaction, with feedback, with rhythm. And though life was still microscopic, it had begun to change the course of the planet forever. By now, the Earth was no longer a raw cauldron of fire and stone. It had cooled, it had oceans, it had an atmosphere that was shifting day by day. And most importantly, it had life, still invisible to the naked eye, but tireless, abundant, and already reshaping the planet in ways that would echo for billions of years. The cyanobacteria that spread across shallow seas were modest in form, just simple cells, but their impact was monumental. By releasing oxygen through photosynthesis, they rewrote the chemistry of oceans and skies. For untold millennia, oxygen seeped into seawater and reacted with dissolved iron, locking it away as layers of rust-red minerals. These banded iron formations, striped red and gray like the pages of an ancient book, became one of the earliest signatures of life's power to transform a planet. But eventually, the oceans could absorb no more. The iron was used up, and oxygen began to accumulate in the air. It wasn't an overnight change. For millions of years, oxygen levels rose and fell, rising slightly, then being consumed by volcanic gases or organic matter. But slowly, the balance tipped. Around 2.4 billion years ago, oxygen crossed a threshold. It began to rise not just locally, but globally. This moment, the Great Oxidation Event, was one of the most profound turning points in Earth's story. For some organisms, oxygen was liberation. It opened the door to new, more powerful ways of extracting energy from food. Instead of relying solely on fermentation or anaerobic pathways, cells could now burn fuel with oxygen, unlocking far more energy. With more energy came the possibility of more complexity. But for others, oxygen was poison. Many of the microbes that had flourished in a low-oxygen world found themselves suffocating in the very waste product their neighbors produced. Entire lineages vanished. The Great Oxidation Event was not just a chemical revolution, it was a mass extinction. And the consequences went beyond life. Oxygen stripped methane from the atmosphere, a potent greenhouse gas that had kept Earth warm beneath a faint young sun. As methane declined, the planet cooled. Ice spread across the globe in one of the earliest snowball Earth episodes. For millions of years, glaciers may have reached the equator, covering oceans in a frozen lid. Yet life persisted. Beneath the ice, hydrothermal vents and pockets of liquid water provided refuge. Microbes clung to survival, and when volcanic carbon dioxide built up enough to thaw the world, they spread again, ready to seize new opportunities. Out of catastrophe came renewal, a theme that would repeat endlessly in Earth's history. The rise of oxygen did something else as well. High in the atmosphere, oxygen formed ozone, creating a protective shield against ultraviolet radiation. This shield allowed life to venture into new environments, shallower waters, and eventually, much later, the land. Oxygen was both a threat and a gift, destructive at first, but ultimately the foundation for everything that followed. Meanwhile, the solid Earth was changing, too. Plate tectonics had grown vigorous. Continents, once small and scattered, began to merge into larger landmasses. Supercontinents formed, broke apart, and reassembled in new shapes. These cycles reshaped climate, altered ocean currents, and stirred the biosphere with fresh challenges and opportunities. Each collision of continents raised mountains, which weathered down, sending nutrients into the seas. Each rift opened new coastlines, shallow zones rich in sunlight and chemistry. Life responded to these changes, diversifying, adapting, and spreading into every niche it could find. By around 1.8 billion years ago, Earth was stable enough to support larger, more complex cells. These were the eukaryotes, organisms with internal compartments and a nucleus to store DNA. Their origins remain mysterious, but many scientists believe they arose through symbiosis. One simple cell engulfed another, and instead of digesting it, they formed a partnership. The engulfed cell became a mitochondrion, a tiny powerhouse, providing energy to its host. Together, they were stronger than either could be alone. This partnership was revolutionary. With mitochondria, eukaryotic cells could use oxygen efficiently, generating far more energy than their simpler cousins. That surplus allowed them to grow larger, to build more complex internal structures, and eventually to form multicellular organisms. From this quiet revolution came the ancestors of every plant, animal, and fungus that would ever exist. But progress was never smooth. For long stretches of time, evolution seemed to pause. Life remained mostly microscopic, cycling slowly through oceans, even as oxygen fluctuated and continents drifted. This long chapter, sometimes called the boring billion, may not have been truly boring. It was a time when biology, geology, and atmosphere were fine-tuning one another. Continents stabilized. The climate cycled. Oxygen levels hovered at low but steady values. And beneath that apparent calm, cells were preparing for the next leap forward. The partnership between cells, the development of new metabolic tricks, the rise of sexual reproduction, all these innovations brewed during this billion-year span. They were quiet revolutions, laying the groundwork for an explosion of diversity to come. And as time flowed on, supercontinents rose and fell. One ancient landmass, called Columbia, assembled from scattered fragments and endured for hundreds of millions of years before breaking apart. Its breakup altered ocean circulation, stirred climates, and opened new shallow seas. Each tectonic cycle acted as a stage, providing new conditions for life to test itself against. Life, geology, and climate were no longer separate stories. They were intertwined, each shaping the others in feedback loops that grew more intricate with time. Microbes altered the chemistry of oceans, which in turn changed how rocks weathered, which influenced atmospheric gases, which fed back into the survival of microbes. The Earth had become a self-regulating system, a network of cycles powered by sunlight, tectonics, and life itself. This was no longer just a planet of rocks and seas. It was a planet where biology and geology co-authored the script, each paragraph written in DNA and stone alike. And though the world of 2 billion years ago would have seemed alien to us, no trees, no animals, no flowers, the seeds of our story were there. Oxygen, complex cells, supercontinents, and the endless cycles of ice and fire had laid the foundation. The next great chapters of Earth's history, the rise of animals, forests, and eventually human beings, would rest upon this deep and ancient groundwork. The Earth of 1.5 to 1 billion years ago was a world of patience. Evolution was working quietly, laying down foundations that would one day support a flourishing web of life. Continents, too, were moving in slow choreography, assembling into supercontinents and breaking apart again, altering climates and shorelines with each new arrangement. One of these vast landmasses was called Rodinia. Born from the collisions of earlier continents, Rodinia gathered nearly all of Earth's land into one immense body. Its coastline stretched across the equator, while inland regions may have been arid deserts. This arrangement profoundly influenced the oceans, restricting currents and creating new environments where life could adapt. Yet the seas of this time remained dominated by microbes. Cyanobacteria still spread across shallow waters, pumping oxygen into the air. Eukaryotic cells, those complex pioneers with nuclei and mitochondria, were diversifying in quiet ways, experimenting with size, shape, and internal structure. Some began forming colonies, clusters of cells that shared labor and resources. These were not yet animals or plants, but they hinted at what was to come. The boring billion, as this era is sometimes nicknamed, may not have been as dull as the name suggests. Beneath the surface, profound innovations were brewing. Sexual reproduction evolved, mixing genetic material between individuals, creating endless variation for natural selection to explore. This genetic shuffling was a game-changer, vastly increasing the potential for complexity and adaptation. At the same time, oxygen levels remained modest. Enough to sustain eukaryotes, but not high enough to fuel rapid expansion. For nearly a billion years, life seemed to plateau, its progress measured in tiny steps rather than dramatic leaps. But in Earth's story, stillness is rarely permanent. Around 720 million years ago, the planet tipped into one of its most extreme experiments, the cryogenian period, when Earth may have frozen over almost entirely. Evidence from rocks in Africa, North America, and Australia suggests that glaciers reached the tropics. If true, Earth was transformed into a snowball world, white from pole to equator. Imagine it, oceans locked beneath kilometers of ice, continents buried under glaciers, skies pale and thin. For life, it was a test of endurance. Most surface habitats would have been wiped away. Yet hydrothermal vents still poured heat into the seas, and cracks in the ice may have left pockets of liquid water where photosynthetic organisms could cling to survival. Life endured in refuges, waiting. Eventually, volcanoes tipped the balance. Eruptions released vast amounts of carbon dioxide, which built up in the atmosphere while the planet lay frozen. With little weathering to draw it down, greenhouse gases accumulated until the ice melted catastrophically. Earth thawed in a global flood, oceans rising, climates swinging violently from cold to hot. These cycles of freeze and thaw repeated more than once, leaving their mark on the planet's rocks and perhaps on its biology as well. Catastrophe often drives innovation, and the cryogenian may have been no exception. When the ice retreated, oxygen levels surged, and ecosystems reorganized. The stage was set for something remarkable. By 635 million years ago, at the dawn of the Ediacaran period, life began to take new forms, large, soft-bodied organisms that sprawled across seafloors. These mysterious creatures, some shaped like fronds, others like discs or quilts, were unlike anything alive today. They left no bones or shells, only impressions in sandstone and silt. For decades, scientists debated whether they were animals, fungi, or an entirely separate experiment in multicellularity. Whatever their identity, the Ediacaran organisms marked a turning point. They were macroscopic, visible to the eye, a world away from the microbial mats that had dominated for billions of years. They may have grazed on microbial films, absorbed nutrients directly from seawater, or even photosynthesized with symbiotic partners. Their existence showed that life was exploring scale, architecture, and ecology in bold new ways. The arrival of these large organisms was made possible by oxygen. After billions of years of gradual buildup, atmospheric oxygen finally reached levels that could support larger, more active bodies. With more energy available, cells could specialize. Colonies became true multicellular organisms, with tissues and organs dividing labor. The Ediacaran seas must have seemed strange, gardens of frond-like beings waving in currents, quilt-patterned mats lying across the seabed, disks and ribbons scattered like alien fossils. They were peaceful ecosystems, slow-moving, without predators as we know them. But they were also fragile. When the world changed again, most of these early experiments vanished, leaving only faint echoes in later life. And then, about 541 million years ago, the curtain rose on one of the most dramatic acts in Earth's story, the Cambrian explosion. In a geological instant, perhaps only 20 million years, life diversified into a stunning array of forms. Creatures with shells, spines, eyes, and legs appeared. Ecosystems grew complex, with predators and prey, burrowers and swimmers, grazers and hunters. The age of animals had begun. The Cambrian explosion was not magic. It was the culmination of billions of years of groundwork. Oxygen provided the energy. Sexual reproduction provided the variation. Multicellularity provided the architecture. Plate tectonics provided shifting environments and nutrient flows. Together, these forces ignited an evolutionary wildfire. The seas filled with trilobites, armored arthropods with compound eyes. Worms tunneled through sediments, stirring ecosystems from below. Sponges filtered water, while early mollusks crept along seafloors. Predators with grasping appendages and sharp vision hunted in open waters. It was the first time ecosystems resembled the intricate webs we know today. The Cambrian explosion left a fossil record so rich that it transformed our understanding of life's history. The Burgess Shale in Canada, the Xinjiang fossils in China, and other sites captured delicate impressions of creatures that would otherwise have vanished without trace. They reveal animals with strange body plans, some with spines like saw blades, others with feathery limbs, still others with features so alien they defy classification. Many lineages would disappear, but others gave rise to groups that still dominate today: arthropods, mollusks, chordates. It's tempting to see the Cambrian as a beginning, but in truth it was a continuation, an acceleration of processes long in motion. The quiet experiments of the Proterozoic, the trials of Snowball Earth, the steady rise of oxygen, all had set the stage. When conditions aligned, life responded explosively. From this point onward, Earth would never again be a microbial world alone. Animals, plants, and fungi would shape the biosphere in ways microbes never could. They would build reefs, graze fields, form forests, and eventually walk on land. The long prelude of Earth's early history had ended. The symphony of complex life was underway. The Cambrian explosion opened a floodgate that would never close. In a blink of geological time, life had gone from simple mats and soft-bodied fronds to seas alive with movement, competition, and innovation. The blueprint of modern ecosystems, producers, consumers, predators, prey, was set in motion. But Earth's story was far from finished. The next chapters would see life expand, experiment, and reshape the very surface of the planet. In the oceans, trilobites scuttled across seafloors in staggering numbers. These armored arthropods were among the most successful groups of the Paleozoic era, evolving into thousands of species that filled every possible niche. Their compound eyes, made of calcite crystals, gave them vision unlike anything before, sharp, faceted, and enduring in the fossil record. They grazed, burrowed, and sometimes even swam, leaving their molted exoskeletons as reminders of growth. Alongside them swam early mollusks, ancestors of clams and squids, experimenting with shells, siphons, and tentacles. Sponges and corals began building the first reefs, modest compared to today's coral cities but already transforming coastlines into havens of biodiversity. Worms tunneled through sediments, stirring nutrients and oxygen deeper into seafloors, forever changing the chemistry of oceans. Predators appeared too, creatures like Anomalocaris, with grasping appendages and a circular mouth lined with teeth. It may have been one of the first apex predators, cruising through Cambrian seas in search of prey. For the first time, life had to run, hide, or defend itself. Hard shells and spines proliferated. Eyes grew sharper. Speed and stealth became weapons. Evolution had found its arms race. Yet the Cambrian was only the opening act of a much longer drama. Over the next 100 million years, ecosystems stabilized and diversified further. By the Ordovician period, beginning around 485 million years ago, the seas were teeming with new life. Trilobites still thrived, but they shared space with brachiopods, shelled creatures that anchored to the seafloor, and with cephalopods, relatives of squids and octopuses that grew into long, armored hunters. Some cephalopods reached lengths of several meters, dominating oceans as apex predators. It was during the Ordovician that the first coral reefs appeared in earnest, built by tabulate and rugose corals. These reefs created three-dimensional habitats, providing shelter for small creatures and hunting grounds for larger ones. Life had discovered the power of engineering, the ability to build structures that reshaped ecosystems. And then, something extraordinary happened. For the first time, life began to venture onto land. At first, it was not animals but plants, or at least their earliest ancestors. Simple green algae adapted to survive in damp soils along coastlines and riverbanks. These pioneers were small, fragile, and dependent on water, but they began the long transformation of continents from barren rock to living landscapes. The Ordovician ended with Catastrophe. A major glaciation locked water into ice, dropping sea levels and collapsing coastal habitats. Many species perished in one of the first great mass extinctions. Yet, as always, life persisted, adapted, and rebounded. The Silurian period, beginning around 443 million years ago, saw the return of stability. Plants spread further inland, evolving vascular systems to transport water and nutrients. Small arthropods, millipede-like detritivores and scorpion-like predators, followed, feeding on decaying matter and one another. Land was no longer sterile. It was becoming an ecosystem of its own. In the seas, jawless fish swam through currents, armored in bony plates. They were the ancestors of vertebrates, the lineage that would eventually give rise to amphibians, reptiles, birds, and mammals. During the Silurian, the first true jaws appeared, transforming feeding forever. Predation became more efficient, ecosystems more dynamic. The Devonian period, beginning about 419 million years ago, is often called the Age of Fishes, and for good reason. Oceans filled with armored placoderms, some reaching lengths of 6 meters, with jaws capable of crushing bone. Sharks appeared, sleek and fast, their design so successful that it has endured almost unchanged to this day. Bony fish diversified into two great groups, ray-finned fish, ancestors of most modern species, and lobe-finned fish, whose sturdy fins contained bones that would one day walk on land. Meanwhile, plants on land underwent their own revolution. They grew taller, stronger, and more complex. The first true forests appeared, with trees like Archaeopteris that reached heights of 30 meters. These forests transformed the atmosphere, drawing down carbon dioxide and pumping out oxygen. Insects followed, buzzing and crawling among the foliage, beginning the intricate relationships between plants and animals that still define ecosystems today. And then came one of the boldest experiments in Earth's history, vertebrates stepping onto land. Lobe-finned fish evolved into amphibians, creatures capable of breathing air and walking with limbs. Fossils like Tiktaalik capture this transition, a fish with both gills and lungs, fins strong enough to support weight, and a flat head suited for peering above water. With this step, the colonization of land was irreversible. The Devonian ended, as so many chapters do, in extinction. Climate shifts, possibly driven by the spread of forests and the drawdown of carbon dioxide, triggered a series of crises that wiped out many marine species. But the survivors carried forward, and in the Carboniferous period, life on land flourished as never before. Carboniferous forests stretched across continents, dense with towering club mosses, horsetails, and ferns. Oxygen levels soared to perhaps 35%, far higher than today's 21%. In this superoxygenated world, insects grew enormous. Dragonflies with wingspans of 70 centimeters buzzed through humid skies. Millipedes longer than a human crawled across forest floors. Amphibians thrived in swamps, while early reptiles, with eggs that could survive away from water, began to spread into drier habitats. These forests also laid down vast beds of organic matter, buried and compressed into the coal seams that humans would one day burn to fuel industry. Long before our arrival, the Carboniferous was writing the script of human history in its sediments. The cycle of rise and fall continued. By the Permian period, beginning around 299 million years ago, continents collided once more to form the supercontinent Pangaea. This vast landmass stretched from pole to pole, altering climate and ocean circulation. Deserts expanded inland, while coastal seas shrank. Reptiles diversified, adapting to arid conditions, and the first ancestors of mammals appeared, small, warm-blooded creatures with differentiated teeth and agile bodies. But the Permian ended in catastrophe greater than any before. Around 252 million years ago, volcanic eruptions in Siberia unleashed vast quantities of lava and gases, warming the climate and suffocating the seas. Methane release may have compounded the effect. The result was the Great Dying, the largest mass extinction in Earth's history. Over 90% of marine species and 70% of terrestrial species vanished. Reefs collapsed. Forests withered. The biosphere nearly unraveled. Yet life endured. From the ashes of the Permian extinction, new lineages would rise, most famously, the dinosaurs. But that is a story for the next act. The Permian extinction nearly silenced Earth's symphony of life. For a time, the world must have felt empty, its once bustling ecosystems reduced to fragile remnants. Seas that had teemed with corals, trilobites, and fish were barren. Forests that had towered for millions of years lay reduced to ash and stumps. But Earth had always been a place of renewal, and in the wake of loss, new forms were waiting to rise. The Triassic period, beginning around 252 million years ago, was the stage for recovery. Slowly, life returned to the seas. Corals reappeared, though of different lineages than before. Mollusks diversified, as did fish and marine reptiles. On land, reptiles spread into niches left vacant by extinction. Among them were the ancestors of turtles, crocodiles, lizards, and eventually birds. The climate of the Triassic was harsh. With most of the continents locked together into Pangaea, vast deserts stretched across the supercontinent's interior. Summers were scorching, winters bitter, rainfall scarce. Yet along coasts and rivers, ecosystems flourished. Amphibians still lingered, but reptiles, with their tough, water-resistant skin and adaptable eggs, began to dominate. It was in this crucible that the first dinosaurs appeared. At first, they were small and unassuming, outnumbered by other reptiles. Some were bipedal hunters the size of dogs. Others were herbivores no larger than turkeys. But their anatomy, lightweight bones, upright posture, efficient lungs, gave them an edge. Over millions of years, they would grow, diversify, and eventually become rulers of the Mesozoic world. Alongside them evolved another important group, the mammals. Descended from synapsid reptiles that had survived the Great Dying, these early mammals were small, nocturnal insect eaters, resembling shrews. They lived in the shadows of dinosaurs, but their agility and warm-blooded metabolisms would ensure their survival through future upheavals. The Triassic ended, like so many eras, in extinction. Around 201 million years ago, massive volcanic eruptions split Pangaea, opening the Atlantic Ocean and releasing carbon dioxide that triggered global warming. Many reptile groups perished. But dinosaurs survived, and in the absence of competition, they flourished. Thus began the Jurassic period, around 201 million years ago, a time of green continents, warm climates, and the true rise of the dinosaurs. Pangaea fractured into northern and southern halves, creating new coastlines and climates. Lush forests of conifers, ferns, and cycads spread across the globe. Insects buzzed through humid air, pollinating primitive plants. Dinosaurs diversified into countless forms. On land, long-necked sauropods grew to immense sizes, browsing treetops. Some, like Brachiosaurus, stood taller than four-story buildings. Predators evolved to match them, from agile hunters like Allosaurus to massive apex predators. Smaller dinosaurs filled every niche, herbivores, scavengers, sprinters, and even feathered species that hinted at the birds to come. In the skies, the first pterosaurs mastered flight. With wings of skin stretched over elongated fingers, they soared above coastlines, catching fish and insects. Some were as small as sparrows, others as large as modern airplanes. Their evolution marked the conquest of the skies, a domain life had never before occupied. The seas, too, were rich with giants. Ichthyosaurs, sleek and dolphin-like, hunted fish in open waters. Plesiosaurs, with long necks and paddle-like limbs, prowled shallower seas. Ammonites, coiled relatives of squids, spiraled through reefs, their shells leaving abundant fossils that still guide geologists in dating Jurassic rocks. Amidst this explosion of reptilian life, mammals remained small but persistent. They burrowed, climbed, and hunted at night, avoiding the giants of the day. Though overshadowed, they were diversifying quietly, experimenting with forms that would one day flourish. The Jurassic world was lush and vibrant, but evolution never rests. By around 145 million years ago, the Cretaceous period began, bringing new landscapes, new ecosystems, and the climax of dinosaur dominance. The Cretaceous was a time of innovation. Flowering plants, or angiosperms, appeared and rapidly spread. Their blossoms attracted insects, forging partnerships that reshaped ecosystems. Pollination became a powerful evolutionary strategy, driving both plant and insect diversity. Forests changed character, becoming richer and more colorful than ever before. Dinosaurs adapted in kind. Herbivores evolved new teeth and jaws to process tougher flowering plants. Hadrosaurs, or duck-billed dinosaurs, developed elaborate crests that may have been used for sound, display, or both. Horned dinosaurs like Triceratops wielded massive frills and horns, possibly for defense but also for communication. Predators such as Tyrannosaurus rex reached terrifying size, apex hunters at the top of food chains. Birds, descended from small feathered theropods, took to the skies in growing numbers. Feathers, once used for insulation or display, had become tools for powered flight. With wings, hollow bones, and sharp vision, birds flourished alongside their dinosaur kin, foreshadowing their survival into the modern age. The seas of the Cretaceous held their own giants. Mosasaurus, a marine reptile, grew to lengths of 15 meters, a predator with jaws capable of crushing anything in its path. Plesiosaurs and ichthyosaurs continued to thrive, though some groups faded. Coral reefs expanded, built largely by modern corals resembling those we know today. Meanwhile, mammals remained small but innovative. Some developed new teeth for diverse diets, others specialized in gliding, burrowing, or climbing. They were not yet dominant, but their quiet resilience would soon prove critical. For over 150 million years, dinosaurs ruled Earth's continents. They adapted to every environment, from deserts to forests to polar regions. Their success was unparalleled. And then, in an instant, it ended. Around 66 million years ago, at the close of the Cretaceous, disaster struck. A massive asteroid, at least 10 kilometers wide, slammed into what is now the Yucatan Peninsula. The impact released energy equivalent to billions of nuclear bombs. A crater more than 150 kilometers across scarred the Earth. The immediate effects were catastrophic: shock waves, tsunamis, wildfires. But the longer aftermath was worse. Dust and sulfur filled the atmosphere, blocking sunlight for months, perhaps years. Photosynthesis collapsed. Plants withered. Food chains unraveled. 75% of all species vanished, including nearly all dinosaurs, pterosaurs, and marine reptiles. Yet not all was lost. Birds, the feathered descendants of small theropods, survived. So did mammals, many of them burrowing or nocturnal, able to withstand the famine and cold. Crocodiles and turtles endured in waterways. Life was battered, but it persisted, ready to rebuild once more. The age of the dinosaurs had ended. The age of mammals was about to begin. When the asteroid fell and the great dinosaurs perished, the world seemed broken. Forests burned, seas darkened, skies filled with ash. For a time, Earth must have felt eerily quiet, its once dominant creatures gone almost overnight. Yet within this silence lay opportunity. The extinction that ended one reign opened the door for another. The survivors were not the largest or most fearsome but the adaptable. Birds endured, inheriting the skies. Crocodiles lingered in rivers and swamps. Turtles, small reptiles, and amphibians held on. But above all, it was the mammals that seized the future. For over 150 million years, mammals had lived in the shadows of dinosaurs. They were small, often nocturnal, feeding on insects, seeds, or whatever scraps they could find. Their diversity was limited, their size constrained by the dominance of reptilian giants. But with those giants gone, mammals expanded into every available niche. The Paleogene period, beginning 66 million years ago, saw the first great flourishing of mammals. Some grew larger, exploring forms that had been impossible before. Within a few million years, the world hosted hoofed grazers, swift carnivores, burrowing rodents, and primates climbing through tropical forests. The age of mammals had truly begun. In the seas, too, mammals claimed their place. Descendants of small, land-dwelling creatures ventured back into the oceans, evolving into whales and dolphins. Early whales, like Ambulocetus, could both walk and swim, bridging the gap between land and sea. Over millions of years, their descendants became fully aquatic, trading legs for flippers, nostrils for blowholes, and small bodies for giants like Basilosaurus, over 15 meters long. On land, ecosystems grew more complex with every passing epoch. In South America, giant flightless birds became apex predators. In North America, early horses the size of dogs grazed open plains. In Asia and Africa, forests sheltered lemur-like primates, precursors to monkeys and apes. The climate of the Paleogene was warm, almost tropical, even near the poles. Lush forests stretched far north and south, housing creatures unlike any alive today. But change was constant. Around 34 million years ago, at the end of the Eocene epoch, Antarctica separated from South America, allowing a new current, the Antarctic Circumpolar Current, to flow around the southern pole. This isolated Antarctica, cooling it dramatically and forming the first great ice sheets of the modern world. As climates cooled, grasslands began to spread. Forests retreated in many regions, replaced by open plains that demanded new adaptations. Herbivores evolved stronger teeth for grinding tough grasses. Carnivores grew faster to chase prey across open ground. The stage was set for familiar forms: horses, antelopes, cats, and dogs. The Neogene period, beginning about 23 million years ago, carried these trends forward. Mammals reached astonishing diversity. Elephants roamed Africa and Asia. Saber-toothed cats hunted in packs. Rhinoceroses grew to towering sizes, some among the largest land mammals ever. Monkeys and apes expanded, adapting to both forest canopies and open savannas. In the oceans, whales continued their transformation, evolving echolocation and baleen to exploit new food sources. The seas that had once belonged to reptiles were now dominated by mammals. And then, in Africa, something remarkable happened. Among the apes, one lineage began to experiment with upright posture. Standing on two legs freed the hands for other uses. Over time, brains grew larger, tools appeared, and cultures began to form. This lineage would eventually call itself human. But long before our species appeared, Earth was already shaping the path. Around 2.6 million years ago, the Pleistocene epoch began, marked by cycles of ice ages. Glaciers advanced and retreated, carving valleys, redirecting rivers, and reshaping continents. In these shifting environments, humans and their ancestors adapted, learning to use fire, build shelters, and form communities. Alongside us lived giants, the megafauna of the Ice Age. Mammoths and mastodons roamed northern plains. Giant ground sloths lumbered through the Americas. Saber-toothed cats hunted across grasslands, while enormous bears stalked forests. These creatures thrived in cold climates, but many would vanish as the ice retreated and humans spread across the globe. The end of the Pleistocene, only about 12,000 years ago, ushered in the Holocene epoch, the slice of time we live in today. With glaciers receding, climate stabilized, and humans flourished. Agriculture arose, civilizations expanded, and the planet entered a new kind of transformation, no longer driven solely by geology or climate, but by the actions of a single species. Looking back, it is humbling to realize how brief our chapter is compared to Earth's vast history. Dinosaurs ruled for over 150 million years. Trilobites thrived for nearly 300 million. Microbes dominated for billions before them. By contrast, humans have walked the Earth for only a heartbeat of geological time. And yet, in that heartbeat, we have changed the face of the planet more profoundly than almost any species before us. We have built cities, altered rivers, reshaped landscapes, and even shifted the chemistry of the atmosphere. In doing so, we have become part of Earth's story not just as participants, but as authors of the next chapter. Some scientists argue that we have entered a new epoch, the Anthropocene, an age defined by human impact. And yet, as powerful as our influence has become, we remain bound by the same cycles that shaped every chapter before us. Tectonics still shifts continents. Volcanoes still breathe fire. Ice still advances and retreats. And the sun, steady yet slowly brightening, still warms the Earth as it has for billions of years. The story of Earth is not finished. It is never finished. Long after we are gone, the planet will continue its rhythms of change, reshaping itself again and again. Life, in some form, will endure. From molten beginnings to oceans of possibility, from the first cells to forests and cities, Earth has been both cradle and crucible. Its history is one of resilience, destruction, renewal, and endless creativity. And we, for a fleeting moment, are witnesses to its song. The story of Earth is not just one of the past, it is also a story of the future. Though our species has only just arrived in geological terms, the planet's rhythms will continue long after us. If we listen carefully to the lessons of deep time, we can begin to imagine what lies ahead, millions and even billions of years from now. In the near future, at least by geological standards, Earth's continents will continue their slow drift. The Atlantic Ocean, still widening today, may one day stop expanding. Subduction zones could form along its edges, drawing seafloor back into the mantle. Africa continues to move northward, pressing into Europe, slowly closing the Mediterranean Sea. Australia drifts north as well, colliding with Southeast Asia. Over the next 100 million years, these movements may culminate in the formation of a new supercontinent. Scientists have proposed several scenarios, with names like Amasia, Nova Pangaea, and Orica. In one vision, the Pacific Ocean closes, bringing the Americas and Asia together. In another, the Atlantic disappears, reuniting the continents into a vast landmass. Whatever form it takes, supercontinents are part of Earth's rhythm, rising and breaking apart every few hundred million years. With new arrangements of land and sea will come new climates. Supercontinents often create harsh, dry interiors, deserts stretching for thousands of kilometers. Coastlines shrink, reducing shallow seas that nurture marine life. Mountain chains rise where continents collide, altering winds and rainfall. Ice ages come and go, as the tilt and orbit of Earth continue their slow cycles. Life will adapt, as it always has, to new challenges and opportunities. Farther into the future, the Sun itself will guide Earth's destiny. Stars like ours brighten gradually over time. In about 1 billion years, the Sun's energy output will be roughly 10% higher than today. That may not sound dramatic, but it will profoundly change the planet. Temperatures will rise, oceans will evaporate more quickly, and the balance of greenhouse gases will shift. The carbonate-silicate cycle, Earth's long-term thermostat, will struggle to keep pace. Increased warmth will speed up weathering, drawing carbon dioxide out of the atmosphere and into rocks. At first, this may seem like a relief, less greenhouse gas to trap heat. But plants depend on carbon dioxide for photosynthesis. As levels decline, forests may wither. Grasses may disappear. Photosynthesis will falter. The green earth we know may fade. Over hundreds of millions of years, oxygen levels may drop as plant life collapses. Animals, too, will dwindle. Ecosystems will contract, leaving behind microbial worlds more like those of the distant past. Earth will not be lifeless, but life may return to forms small, simple, and resilient, hidden in niches where conditions remain tolerable. 2 billion years from now, the oceans themselves may be gone. Rising solar energy will drive a runaway greenhouse effect, evaporating seas into the sky. Water vapor, a potent greenhouse gas, will trap more heat, accelerating the process. Eventually, hydrogen from water molecules will escape into space, leaving Earth dry and barren. By then, Earth may resemble Venus more than the blue planet we know. Temperatures will soar. Clouds will shimmer with steam. Rocks will bake beneath a relentless sun. Life, if it clings on at all, may survive only underground, in caves or deep within the crust, where traces of water remain. And yet, even this is not the end of Earth's journey. In about 5 billion years, the Sun itself will swell into a red giant. Its outer layers will expand outward, engulfing Mercury and Venus, and perhaps even Earth. If Earth is consumed, the planet's story will end in fire, its atoms scattered into space. If it survives, it will be scorched, its surface sterilized, orbiting a dying star. Eventually, the Sun will shed its outer layers, leaving behind a dense white dwarf, an ember of a star, slowly cooling for eternity. Earth, if it still orbits, will circle a pale remnant, its long story written in silent rock. But Earth's atoms will not vanish. They will be carried outward, recycled into interstellar clouds. Someday, perhaps billions of years later, those clouds may collapse into new stars, new planets, new beginnings. The carbon in our bones, the oxygen in our breath, the iron in our blood, all forged in ancient stars, will once again join the cycle of creation. When we look at the night sky, we are reminded that Earth's story is not unique. Billions of planets orbit billions of stars. Some are barren, others fiery, others frozen. Perhaps some host life. Perhaps some will rise to civilizations. The rhythms of geology, biology, and time are universal, written into the very fabric of the cosmos. Our chapter, Here and Now, is short. Humanity has existed for only a few 100,000 years, civilization for only a few thousand. And yet, in this instant, we have the rare gift of reflection. We can trace Earth's story from molten birth to green forests, from the first raindrops to towering mountains, from microbial whispers to the roar of cities. We can imagine its future, long after we are gone. Perhaps that is our role in this immense story, not just to live upon Earth, but to remember it, to tell it, to pass along the wonder of a planet that has endured for 4.5 billion years. A planet that has been lava and ice, ocean and desert, cradle and crucible. A planet that, for a brief moment, carries us. So when you step outside and feel the ground beneath your feet, when you breathe the air, when you look up at the stars, remember that you are part of this story. The atoms in you were born in ancient stars, carried through eons of Earth's history, and will one day continue into the future beyond imagining. The Earth is old, but it is not finished. Its song continues, and we, for now, are listening.